Now in this lecture we'll answer on two questions. In the first question we find out the area of this circle that is inscribed by this trapezoid ABCD, and in the second question we find out the length of this line segment QB that is equal to x. So we'll start with the first question. In the drawing we have trapezoid ABCD that blocks this circle. Trapezoid is a quadrilateral with one pair of parallel sides. This trapezoid ABCD, side AD is parallel to side BC. So trapezoid ABCD blocks this circle, or this circle is inscribed by trapezoid ABCD. In addition, you know that this is 9 7 AM, that is equal to A units in Islam. This is 9 7 MB, that is equal to B units in Islam. Again, our mission is to find out the area of this circle. So first of all, we define the center of this circle. This point is point O. We define the point of tendency of tangent AD with this circle. This point is point P. And we define the point of tendency of tangent BC with this circle. This point is point Q. So here we can implement rule 2, so I repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle. This is the common standpoint point P. From this common standpoint point P we have two tangents to this circle. Tangent PA and tangent PB. And according to this one, rule 2, they are equal to each other. That is to say PA equals to PB. So we can actually implement rule 2 in our drawing. Also in our drawing, if we focus on this common standpoint point A, from this common standpoint point A, we have two tangents to this circle, tangent AM and tangent AP. And according to rule 2, they are equal to each other. That is to say AM equals to AP. But AM equals to A according to what's given in the question, therefore AP must be also equal to units in its length. Likewise, we focus on this common standpoint point B. From this common standpoint point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM equals to B units in its length according to what is given in the question. Therefore, BQ must be also equal to B units. BQ equals to B units in its length according to rule 2. In the next step, we will define the radius of this circle as x, and we will join points O and Q together by a straight line. So point O is the center of the circle, point Q is the point of the circle itself. Therefore, OQ is the radius of this circle that is equal to x according to our definition. And because of the fact that the radius that the radius of Q is drawn to point Q, that is the point of tendency of tangent BC with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and P together by a straight line. OP is of course the radius of this angle, that is equal to x. Here you can also implement rule 1 because of the fact that the radius OP is equals to x. The radius OP is drawn to point P, that is the point of tendency of tangent AD with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So in the next step, we will do a construction, that is to say, from point A, we will go perpendicular on BC. Again, from point A, we will go perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point N. By doing this construction, we're going to do those two angles. Those two angles are located between the power lines AD and BC. AD is parallel to BC because ABCD is a trapezoid. So those two angles are located between the power lines AD and BC, and therefore they are defined as one-sided interior angles. And according to rule 17, the sum of two one-sided interior angles that are located between parallel lines is equal to 180 degrees. So on page 50 on rule 17, according to rule 17, the sum of one-sided interior angles that are located between two parallel lines is equal to 180 degrees. So in the moment we have line A that is parallel to line B. This is the right line C that intersects with those two parallel lines A and B, those 2 points. Those are angles alpha and beta that are defined as one-sided interior angles. And because of the fact that those two one-sided interior angles are located between the parallel lines A and B, the sum of those two one-sided interior angles must be equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. So as I mentioned before, we can implement here rule 17. Why? We can implement here rule 17 because of the fact that those two one-sided interior angles are located between the parallel lines AD and BC, and therefore the sum of those two one-sided interior angles must be equal to 180 degrees. So this angle is a right angle according to our construction. It is equal to 90 degrees in its size, so 90 degrees plus the size of this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 17. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do another construction. That is to say, from this point O, that is the center of this circle, we will go perpendicular on AN. Again, from point O, we will go perpendicular on AN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. we define the touching point of the perpendicular from point O and AN. This point is point T. By doing this construction, we created the small polyhedron AT OP. Inside this small polyhedron AT OP, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Likewise, in the lower quadrilateral TOQN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees, according to the same rule that I mentioned, that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So in total, the size of the big angle POQ, the size of this big angle POQ is equal to 90 degrees plus 90 degrees, that is 180 degrees. So right now, the size of the big angle POQ is equal to 180 degrees. And you know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, a line segment POQ is a straight line. So this is line segment POQ. It is a straight line. If POQ is a straight line, then PQ is also a straight line. PQ is a straight line. So actually, shape APQN, this shape APQN consists of 4 sides. 1, 2, 3, 4. So write it down. Shape APQN consists of 4 sides, and therefore shape APQN is a quadrilateral. So shape APQN is a quadrilateral because it consists of 4 sides. But we already found out that in quadrilateral APQN we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral APQN as a rectangle because it has 4 right angles. So I write it down. Quadrilateral APQN is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So actually, in rectangle APQN, side AP must be equal to the opposite side NQ. But AP is 8, therefore NQ must be also equal to A units in its length. Likewise, according to the same rule, in the same rectangle APQN, side PQ must be equal to the opposite side AN. But PQ in total equals to x plus x, that is 2x. Therefore, AN must be also equal to 2x units in its length. So, this is the opposite side AN is actually equal to 2x units in its length. What is the length of this missing 97BN? From the drawing, it is very easy to see that BN in total equals to BQ minus NQ. Again, BQ minus NQ equals to BN. So, I'll write it now. BN equals to BQ minus NQ. So, BN in total equals to BQ. BQ is B according to rule 2. Minus NQ. Just like now found that NQ equals to A. So in total, BN equals to B minus A units in its length. This side BN equals to P minus A units in its length. In the next step, I'll copy the right angle triangle A and B in a new page, and we will implement the Pythagoras theorem on this right angle triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a abbreviation for Pythagoras theorem. The hypotenuse AB equals to A plus B units in its length. We just right now found out that NB equals to B minus A, and AN equals to 2x. So actually, this is the right triangle A and B that occurs on the original drawing. In this right triangle A and B, according to the Pythagoras theorem, AB square, that is the square of the hypotenuse, equals to AN square plus NB square. So I'll write it down. So AB square, that is the square of the hypotenuse, is equal to AN square plus BN square. AB is A plus B, therefore AB square is A plus B square, and it is equal to AN square. AN is 2x, therefore AN square is 2x squared. 2x squared is 4x squared plus Bn square. Bn is B minus A, therefore Bn square is B minus A square. So in total we found out that A plus B square equals to 4x square plus B minus A square. Here we will open the brackets on both sides of this equation, and we get that A plus B square is equal to A square plus B square plus 2 times A times B, and it is equal to 4x square plus b minus a squared. B minus a squared equals to b squared plus a squared minus 2 times a times b. So total, we found out that a squared plus b squared plus 2ab equals to 4x squared plus b squared plus a squared minus 2ab. So here we have a squared on both sides of the equation, so a squared gets cancelled. And we have also b squared on both sides of this equation, so b squared also gets cancelled. After we cancel those two expressions, in this side of the equation we have to leave with 2ab. On the other side of the equation we have 4x squared minus 2ab. So here we will add 2ab to this equation, and we will get that 2ab plus 2ab is 4ab, so 4ab equals to 4x squared. Here we divide this equation by 4, and we get that 4ab over 4 is ab. So ab equals to 4x squared over 4 is x squared. So in total we found out that x squared equals to ab. Our mission is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Okay, again, the area of any circle is equal to pi times the radius of the circle squared. And therefore, the area of our circle must be pi times the radius of our circle squared. The radius of our circle is x, therefore the radius squared is x squared. So in total we found out that the area of our circle is pi x squared. But so it is pi times x squared. We just right now found out that x squared equals to ab. So we substitute x squared here by ab. So in total we found out that the area of our circle is pi ab. The area that we are looking for in this question, that the area of this circle is equal to pi ab square units. And that is the answer to the question. Okay, again, we found out that the area of this circle is equal to pi times ab square units. So we finish with the first question. In the next step, I'll present you the second question and we'll solve the second question of this lecture. Our mission in this second question is to find out the length of this line segment QB that is equal to x. So we have to find out the value of x. So actually in the drawing we have a semicircle. We know that AB equals to 30 units in its length. AB is the diameter of this semicircle, so the diameter of this semicircle is equal to 30 units in its length. In addition, we know that this is called PA, that is equals to 10 units in its length. This is called PQ, that is also equals to 10 units in its length. And our mission is to find out the length of this chord QB, that is equals to x. We have to find out the value of x. So first of all, we will define the center of this semicircle. This point is point O. The diameter of this semicircle is 30, therefore the radius must be equal to half of it. That is to say, the radius must be equal to 30 over 2, that is 15. So the radius of this semicircle is equal to 15 units in its length. Point O is the center of this semicircle. Point A is the point of the semicircle itself, therefore OA is the radius of this semicircle. that is equal to 15 units in its length. Likewise, OB is also the radius of the semicircle, that is equal to 15 units. In the next step, we join points O and P together by a straight line. Point O is the center of the semicircle, point P is the point of the semicircle itself. Therefore, OP is the radius of this semicircle, that is equal to 15 units in its length. In the next step, we'll complete this semicircle to a circle. And we will extend the radius PO by a straight line until it touches the circle at this point. We will define the touching point of the extended radius PO with this circle. This point is point M. We will join points B and M together by a straight line. OM is of course the radius of this semicircle, that is equal to 15 units. Those two angles are defined as vertex angles. We know that vertex angles are equal to each other. So if this angle is theta, then this angle must be also equal to theta, because those two angles are equal to each other according to the rule that I mentioned. So in the next step, we will prove that this triangle APO can go into this triangle MBO. So we prove that those two triangles can go into each other. So why those two triangles can go into each other? First of all, side PO of this triangle APO is equal to side OM of this triangle OMB. They are both the radius of the circle, therefore they are equal to each other. So I write it down. PO equals to OM. And again, side PO of triangle APO is equal to side OM of triangle OMB. They are both the radius of the circle, that is equal to 15, therefore they are equal to each other. In addition, those two angles are both equal to theta, therefore they are equal to each other. Actually, they are equal to each other according to the rule that vertex angles are equal to each other. So actually, this is angle AOP. In triangle AOP, and it is equal to this angle, that's actually angle MOB. So they are both equal to theta, therefore they are equal to each other. Okay, again, angle AOP of triangle APO equals to angle MOB of triangle OMB. They are both equal to theta, therefore they are equal to each other according to the rule that vertex angles are equal to each other. And finally, side AO of this triangle APO is equal to side OB of this triangle OMB. They are both the radius of the circle, therefore they are equal to each other. So I write it down. OA equals to OB. And again, side OA of triangle APO is equal to side OB of triangle OMB. They are both the radius of the circle, that is equal to 15, therefore they are equal to each other. So actually proves that those two triangles can go into each other according to side angle side rule. What is side angle side rule? Actually, we have those two sides and the angle that is included between those two sides in triangle APO correspondingly equal to those two sides and the angle that is included between those two sides in triangle OMB. Therefore, those two triangles can go into each other according to side angle side rule. So I'll write it down. So I actually found out that triangle APO congruent, this is the sign of congruent, to triangle OMB according to side angle side rule. And from the fact that those two triangles can go into each other, we will derive that side AP or triangle APO is equal to side MB or triangle OMB. And again, we derive that AP equals to MB according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AP and MB, must be also equal to each other. But we know that according to what is given as the question, PA equals to 10 or AP equals to 10. So we can write here that AP equals to 10, and from this equation 10 equals to AP equals to MB. We will derive that MB is also equal to 10 units in its length. MB equals to 10 units. This is called PM. Chord PM passes through point O, that is the center of this circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. So PM is the diameter of this circle. In the next step, I'll copy the semicircle with the diameter PM, and we will analyze this semicircle. So actually this is the semicircle with the diameter PM that I copied from the original drawing. PQ equals to 10 units in its length according to what is given as the question. We have already found out that MB also equals to 10 units. PO equals to OM, above the radar of the circle, therefore they are equal to each other. And QB equals to X, that is the line segment that we are looking for in this question. Repeat again that QP equals to BM, they are both equal to 10 units in their lengths. So in the next step, we will extend line segment PQ and line segment MB until they intersect with each other. Okay, this is their touching point or their intersection point. We define this point as point E. Actually, we extended those two line segments that are equal to each other in their lengths until they intersect with each other at point E. Whenever you extend two line segments with the same lengths until they intersect with each other, then the new extended line segments must be also equal to each other in their lengths. We extended line segment MB and line segment PQ, and we got the new line segment that is PE and ME. According to the rule that I mentioned, PE must be also equal to ME. Again, according to the rule that I mentioned, PE must be also equal to ME. So actually, we have here triangle PEM. In triangle PEM, PE is equal to EM. Therefore, it is an isosceles triangle. And note that the angles of the bases of the isosceles triangle are equal to each other. That is to say, those triangles that are defined as the angle of the base are equal to each other. Anyway, I prove that those two angles are equal to each other. We have the rule that in front of equal sides in the triangle, there are equal angles. We know that EP equals to EM. In front of this side EP, we have this angle. That's actually angle PME. In front of this side EM, we have this angle. This is actually angle MPE. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta, because they are equal to each other according to the rule that I mentioned. In the next step, we will complete this semicircle to a circle. So now we have here this quadrilateral PQBM that is inscribed by this circle. And according to rule 16, any quadrilateral that is inscribed by a circle, the sum of its two opposite angles is equal to 180 degrees. So repeat again rule 16. According to rule 16, if a quadrilateral is inscribed by a circle, then the sum of its two opposite angles is equal to 180 degrees. This is quadrilateral ABCD and is inscribed by this circle. Those are defined as opposite angles of quadrilateral ABCD. And according to this rule 16, the sum of those two angles is equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. Likewise, those two angles are also defined as opposite angles, and according to this rule 16, the sum of those angles must be equal to 180 degrees. That is to say, angle 1 plus angle 2 equals to 180 degrees. So can I actually implement rule 16 in our drawing? As I mentioned before, because of the fact that we have here quadrilateral PQBM is inscribed by this circle. The sum of its two opposite angles must be equal to 180 degrees according to rule 16. Those are the two opposite angles of this quadrilateral PQBM, and according to rule 16, the sum of those two angles must be equal to 180 degrees. This angle equals to beta. So beta plus this missing angle, in total the sum of those two angles must be equal to 180 degrees, according to rule 16. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of those two opposite angles in a quadrilateral QPMB that is inscribed by this circle according to rule 16. Likewise, those two angles are also defined as opposite angles, and according to rule 16, the sum of those two angles must be equal to 180 degrees. This angle equals to beta. So beta plus this missing angle in total must be equal to 180 degrees. Therefore, this missing angle must be equal to 180 degrees minus beta. Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of those two opposite angles according to rule 16. So here we have those two angles. This is angle beta and this is angle 180 degrees minus beta. The sum of those two angles, 180 degrees minus beta plus beta, is 180 degrees. So the sum of those two angles is 180 degrees. But those two angles are defined as one-sided interior angles. And whenever the sum of two one-sided interior angles is equal to 180 degrees, then those two one-sided interior angles must be between parallel lines. That is to say, in this case, QB must be parallel to MP. Again, QB or BQ must be parallel to MP, according to rule 18. So I'll repeat quickly on rule 18. According to rule 18, if the sum of two one-sided interior angles is equal to 180 degrees, then they are located between two parallel lines. In the drawing, we have line A that is parallel to line B. Line C intersects with those two parallel lines at those 2 points. Angles alpha and beta are defined as one-sided interior angles. And we know that alpha plus beta is equal to 180 degrees. So if alpha plus beta is equal to 180 degrees, then line A must be parallel to line B. Again, if alpha plus beta, that is the sum of those two interior angles. If the sum of those two angles is 180 degrees, then line A must be parallel to line B. We actually have only implemented rule 18 in our drawing, because we know that the sum of those two angles is 180 degrees and they are defined as one-sided interior angles. And whenever the sum of one-sided interior angles is 180 degrees, then they must be between two parallel lines. That is to say, BQ is parallel to MP. Again, BQ is parallel to MP according to rule 18. So I write it down. So we found out that QB, BQ or QB is the same. QB is parallel to PM according to rule 18. So in the next step, I'll copy again this semicircle with the diameter PM, and we will continue to analyze this semicircle. But again, that QB is parallel to PM according to rule 18. So here, this is the semicircle with the diameter PM that I copied from this drawing. Here, we join points O and Q together by straight line. Point O is the center of the semicircle, point Q is the point on the semicircle itself, therefore Q is the radius of this semicircle, this is equal to 15 units in its length. Likewise, we will join points O and B together by straight line. OB is also the radius of this semicircle, that is equal to 15 units in its length. Those two angles are defined as alternating angles, and they are located between the parallel lines QB and PM. According to rule 18, QB is parallel to PM. But again, those two angles are defined as alternating angles and are located between the parallel lines QB and PM, and therefore they must be equal to each other according to rule 15. So, repeat quickly rule 15. According to rule 15, alternating angles between parallel lines are equal to each other. In the drawing we have line A that is parallel to line B. This is line C that intersects with those two parallel lines A and B at those 2 points. Those are angles alpha and beta that are defined as alternating angles. And according to this rule 15, those two angles alpha and beta that are defined as alternating angles, they are located between the parallel lines A and B. And therefore they are equal to each other. That is to say, alpha equals to beta. So we can actually implement rule 15 in our drawing. Why? Because in our drawing it's a one dimension. Those two angles are defined as alternating angles and are located between the parallel lines QB and PM, and therefore they are equal to each other according to rule 15. So if we define this angle as beta, then this angle must be also equal to beta because they are equal to each other according to rule 15. In the next step, I will present to you the law of cosines, and we will implement the law of cosines in this green triangle, triangle PQO. And in this white triangle, triangle QOB. So what is the law of cosines? First of all, the law of cosines is true in any triangle. This is triangle ABC, that could be any triangle. This triangle ABC, side AB equals to A units in itself, side AC equals to B units in itself. This is side BC, that is equals to C units in itself. This is angle theta. So in this triangle ABC, that could be any triangle. Cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, in this triangle ABC, that could be any triangle. Cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So in the next step, we'll implement this law, the law of cosines, in this green triangle PQO. So I'll copy the green triangle PQO in a new pattern. We will implement the law of cosines in this green triangle. This is angle beta, it's also angle POQ. Side PQ equals to 10 units in its length. Side PO equals to 15 units in its length. And side QO also equals to 15 units in its length. And this is angle beta. So actually, this is the green triangle PQO that according to the original drawing. In the next step, we will implement the law of cosines on this triangle PQO. So according to the law of cosines, in this triangle PQO, cosine beta equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. This is equation 1. So according to the law of cosines, in this triangle PQO, cosine beta equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. In the next step, I'll copy this white triangle QOB. In a new pattern, we will implement the law of cosines on this triangle QOB. Okay, this is diagonal QOB. With a copy from this drawing. In this triangle QOB, according to the law of cosines, this will be equation 2, cosine beta equals to 15 squared plus x squared minus 15 squared over 2 times 15 times x. I'll repeat again, in this triangle QOB, according to the law of cosines, cosine beta equals to 15 squared plus x squared minus 15 squared over 2 times 15 times x. So we have two equations for cosine beta. This is equation 2, but also this is equation 1 for cosine beta. Therefore, we create equation 3 that states that cosine beta, according to equation 1, must be equal to cosine beta according to equation 2. Okay? So, cosine beta according to equation 1 equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. So this is the expression of cosine theta according to equation 1. And it must be equal to cosine beta according to equation 2. Here, this is the value of cosine beta according to equation 2. That is actually 15 squared plus x squared minus 15 squared divided by 2 times 15 times x. And again, this equation 3 states that cosine theta according to equation 1 must be equal to cosine theta according to equation 2. We have in the denominator of those two expressions 2 times 15, 2 times 15. So 2 times 15 will get cancelled. In this side of the equation, we have 15 squared minus 15 squared is of course 0. So here we're left only with x squared over x. X squared over x is x, of course. So in this side of the equation we're left only with x. While on the other side of this equation 3 we have 15 squared plus 15 squared minus 10 squared divided by 15. So in total, if you found out that according to equation 3, x equals to 15 squared plus 15 squared minus 10 squared divided by 15. So x equals to 15 squared. 15 squared is 225, so 225 plus 15 squared, that is 225. 225 plus 225 is 450 minus 10 squared. Minus 10 squared, 10 squared is 100, so it is minus 100 over 15. So if we found out that x equals to 450 minus 100 over 15. So x equals to 450 minus 100 is 350 over 15. So x equals Here we divide both the numerator and the denominator of this number by 5. So 350 over 5 is 70, and 15 over 5 is 3. So in total we found out that the length of line segment QB that is equal to x, it is equal to either 70 over 3 units in its length, or in terms of numbers, 70 over 3 is 23 and 3rd units in its length. Repeat again, if we found out that the length of this line segment QB that is equal to x, it is equal to either 70 over 3 units in its length, or in terms of numbers, the length of line segment QB that is equal to x is equal to 23 and 3rd units in its length. So we finished with the second question. In the next step, I'll summarize the lecture. I'll start with the first question, of course. Our mission in this first question is to find out the area of this circle that is inscribed by this trapezoid ABCD. The definition of a trapezoid is a quadrilateral with one pair of parallel sides. Again, a trapezoid is a quadrilateral with one pair of parallel sides. In this trapezoid ABCD, side AD is parallel to side BC. So in the drawing, we have trapezoid ABCD that blocks this circle. In addition, you know that this is line segment AM that is equal to A units in its length. This is line segment MB that is equal to B units in its length. Again, our mission is to find out the area of this circle. So in the first step, we define the center of this circle. This point is point O. We define the point of tendency of tangent AD with this circle. This point is point P. And finally, we define the point of tendency of this tangent BC with this circle. This point is point Q. Here we can implement rule 2. Why? Because we have here, this is the common extent point A. From this common extent point A, we have two tangents to this circle, tangent AP and tangent AM. And according to rule 2, they are equal to each other. That is to say, AP equals to AM. But AM is A, according to what is given in the question, therefore AP must be also equal to A units in its length. Likewise, if you focus on this common extent point B, from this common extent point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM is B according to what is given in the question. Therefore, BQ must be also equal to B units in its length. In the next step, we join points O and Q together by straight line. And we define the radius of this circle as x. Point O is the center of this circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle, that is equal to x according to our definition. And because of the fact that the radius of Q that is equal to x, the radius of Q is known to point Q, that is the point of tendency of tangent BC in this circle, and whenever you have a radius that is known to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and P together by straight line. OP is of course the radius of this circle that is equal to x, and because of the fact that the radius OP that is equal to x, the radius OP is known to point P, that is the point of tendency of tangent AD with this circle, and whenever you have a radius that is known to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, all 1. In the next step, we did the construction, that is to say, from this point A, we draw perpendicular on BC. Again, from point A, we draw perpendicular on BC. So clearly this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC, this point is point N. By doing this construction, we can deduce those two angles that are defined as one-sided interangles and are located between the bound lines AD and BC. Why AD is parallel to BC? Because ABCD is a trapezoid. Therefore, AD is parallel to BC. So those two one-sided interangles are located between the bound lines AD and BC, and therefore the sum of those two one-sided interangles must be equal to 180 degrees. So 90 degrees plus the size of this angle, in total the sum of those two angles must be equal to 180 degrees according to rule 17. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we did another construction. That is to say, from this point O, we draw perpendicular on AN. Again, from point O, we draw perpendicular on AN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AN. This point is point T. By doing this construction, we can do quadrilateral APOT. Inside this quadrilateral APOT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this four faces again, in total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this four faces again must be equal to 90 degrees in its size. Likewise, inside this quadrilateral TOQN, we have 1, 2, 3 right angles. Again, the sum of 3 right angles is 270 degrees. So 270 degrees plus the size of these four faces again, in total they must be equal to 360 degrees. Therefore, these four faces again must be equal to 90 degrees in its size. So, the big angle POQ in total is equal to 90 degrees plus 90 degrees, that is 180 degrees. Repeat again. The big angle POQ is equal to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in size, it is defined as a straight line. Therefore, line segment POQ is a straight line. Line segment POQ is a straight line. If line segment POQ is a straight line, then line segment PQ is also a straight line. Here PQ is also a straight line. And therefore, in this shape APQN consists of four sides. 1, 2, 3, 4. And therefore, shape APQN is a quadrilateral. Shape APQN consists of four sides, and therefore it is a quadrilateral. Shape APQN is a quadrilateral. But we have already found out that in quadrilateral APQN we have four right angles. And according to rule 5, any quadrilateral that says 4 right angles must be this rectangle in front of the square. So we relate to this quadrilateral APQN as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle APQN, side AB must be equal to the opposite side NQ. But AP is Z, therefore NQ must be also equal to a unit in its length. Likewise, according to the same rule, in the same rectangle APQN, side PQ must be equal to the opposite side AN. But PQ in total is x plus x, that is 2x, therefore AN must be also equal to 2x units in its length. What is the length of this missing line segment? BN equals to BQ minus NQ. Again, BN equals to BQ minus NQ. BN equals to BQ minus NQ. So BN equals to BQ, BQ is B, minus NQ, NQ is A. So in total, BN equals to B minus units in its length. In the next step, I copy this right triangle A and B In the equation, implemented the Pythagoras theorem on this right angle, triangle A and B. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So this is the right triangle, triangle A and B that according to the original drawing. This right triangle A and B, according to the Pythagoras theorem, AB squared, that is the square of the hypotenuse, equals to AN squared plus BN squared. AB is A plus B, therefore AB squared is A plus B squared, and it is equal to AN squared. AN is 2x, therefore AN squared is 4x squared plus BN squared. BN is B minus A, therefore BN squared is B minus A squared. So in total, you should find out that A plus B squared equals to 4x squared plus B minus A squared. We open the brackets on both sides of this equation, and we shall find out that A plus B squared equals to A squared plus B squared plus 2 times A times B. And it is equal to 4A squared plus B minus A squared. B minus A squared equals to B squared plus A squared plus 2 times A plus 2 times A times B. So in total we shall find out that A squared plus B squared plus 2AB equals to 4x squared plus B squared plus A squared plus 2 times A times B. So here we have A squared on both sides of this equation, so A squared we get cancelled. We have also B squared on both sides of this equation, so B squared also will get cancelled. After we cancel those two expressions, in this side of the equation we left only with 2AB. On the other side of the equation we left with 4x squared plus 2AB. So in total we actually found out that 2AB equals to 4x squared minus 2AB. Here we added 2AB to this equation, and we found out that 2AB plus 2AB is 4AB, so 4AB equals to 4x squared. Here we divided this equation by 4 and finally found out that 4AB over 4 is AB and 4x squared over 4 is x squared. So in total we found out that x squared equals to AB. Our mission is to find out the area of this circle. Actually we know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of this circle must be equal to pi times the radius of this circle squared. The radius of this circle is x, therefore the radius squared is x squared. So in total we found out that the area of this circle is equal to pi x squared. We just right now found out that x squared equals to AB, so we can substitute x squared here by AB. We did it, and we found out the area of the circle is equal to pi AB. So if we found out that the area of this circle, that is the area that we are looking for in this question, is equal to pi times AB square units. We finished with the first question. In the next step, I will do the second question, and we solve the second question of this lecture. In this second question, our mission is to find out the length of this line segment QB that is equals to x. We have to find out the length of QB that is equals to x. So we have to find out the value of x. So in the domain, in the original domain, we have a semicircle. This is the chord PA that is equals to 10 units in length. This is called P cube that is also equals to 10 units in length. This is line segment QB that is equals to x units in its length, and our mission is to find out the length of QB that is x. We have to find out the value of x. In addition, we know that AB equals to 30 units in its length. AB is the diameter of the semicircle. So we know that the diameter of the semicircle is 30 units. So we define the center of the semicircle. This point is point O. If the diameter is 30, the radius must be equal to half of it. That is to say, the radius must be equal to 30 over 2, that is 15. So the radius of this semicircle is 15. Point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore, always the radius of this semicircle is the radius of the semicircle, that is 15 units. OB is also the radius of the semicircle, that is 15. We join points O and P together by straight line. Point O is the center of the semicircle, point P is the point of the semicircle itself, therefore OP is also the radius of the semicircle, that is 15 units in its length. In the next step, we completed this semicircle to a circle, and we extended the radius PO until it touches the circle at this point. We find the touching point of the extended radius PO with this circle. This point is point M. OM is of course the radius of this circle, that is equal to 15 units in its length. In the next step, we join points M and B together by a straight line. those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if this angle is theta, then this angle must be also equal to theta, because they are equal to each other according to the rule dimensions. In the next step, we prove that this triangle APO is congruent to this triangle OBM. So why those two triangles congruent to each other? First of all, side PO equals to side OM. Side PO of triangle APO equals to side OM of triangle OMB. They are both the radii of the circle, therefore they are equal to each other. In addition, those are angles are defined as vertex angles, and we know that vertex angles are equal to each other. And finally, side AO of triangle APO is equal to side OB of triangle MO. Again, side AO of triangle APO is equal to side OB of triangle OMB. They are both the radii of the circle, is equal to 15, therefore they are equal to each other. So I shall prove that those two triangles can go into each other according to side angle side rule. We have those two sides, and the angle that is included between those two sides in triangle MOB are correspondingly equal to those two sides, and the angle that is included between those two sides in triangle POA. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we will derive that side PA is equal in triangle APO is equal to side MB in triangle OMB. Again, we derive the side AP equals to side MB. According to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding sides must be also equal to each other. But AP is 10 according to this equation. So we can write here that AP equals to 10, and from this equation 10 equals to AP equals to MB, we will derive that MB is also equal to 10 units in its length. If MB equals to 10 units in its length. We know that this is called PM that passes through point O, and any chord of point O that is the center of this circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, PM is the diameter of this circle. In the next step, I complete this semicircle with the diameter PM, and we analyze this semicircle. Actually, this is the semicircle with the diameter PM. OP equals to OM. Above the radii of the semicircle is equals to 15. PQ equals to 10 units in its length, MB also equals to 10 units in its length, and QB is the line segment that we are looking for in this question. So chord PQ equals to chord MB. They are both equal to 10 units, therefore they are equal to each other. In the next step, we extended those two equal chords by a straight line until they intersect with each other. This is the intersection point, and we have the rule that whenever you extend two equal line segments, then the extended line segments must be also equal to each other in their lengths. Again, when you extend two equal line segments, then the extended line segment must be also equal to each other in their lengths. Here, line segment PQ equals to line segment MB. We extended those two line segments, and we got the new line segments. The extended line segments are PE and EM. So PE also must be also equal to ME according to the rule that I mentioned. So in triangle PEM, PE equals to EM, therefore triangle PEM is an isosceles triangle, and we know that those are the two angles that are defined as the bases of the angles of the base, and therefore they are equal to each other. Anyway, I actually proved why those two angles are equal to each other. We have the rule that in front of equal sides there are equal angles. In front of this side PE we have this angle, in front of this side EM we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta. Okay. In the next step, We completed this semicircle to a circle. So in the drawing we have quadrangle PQBM that is inscribed by this circle. And we know that according to rule 16, any quadrangle that is inscribed by a circle, the sum of its two opposite angles is equal to 180 degrees. Again, any quadrangle that is inscribed by a circle, the sum of its two opposite angles is equal to 180 degrees. So quadrangle PQBM is inscribed by this circle, and therefore the sum of those two opposite angles must be equal to 180 degrees. But this is angle beta, so angle beta plus the size of this angle in total must be equal to, the sum of those angles must be equal to 180 degrees according to rule 16. Therefore this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. It is the sum of the opposite angles in this quadrangle PQBM that is inscribed by this circle according to rule 16. Likewise, the sum of those angles must be also equal to 180 degrees. Therefore, this is angle beta. Therefore, this missing angle must be equal to 180 degrees minus beta. Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of those two opposite angles in quadrangle PQBM. So we found out that this is the angle beta and this is angle 180 degrees minus beta. Angle 180 degrees minus beta plus beta is 180 degrees. So the sum of those two one-sided interangles is equal to 180 degrees. And according to rule 18, whenever you have two one-sided interangles that the sum of them is equal to 180 degrees, then they must be between parallel lines. And because of the fact that the sum of those two one-sided interangles is equal to 180 degrees, they must be between the parallel lines. That is to say, QB is parallel to PM. Again, QB is parallel to PM according to rule 18. Okay, in the next step I copy it again, this semicircle with the diameter PM, and continue to analyze this semicircle with diameter PM. So this is the semicircle with the diameter PM. Point O is the center of this semicircle. Therefore OP equals to OM. They're both the radius of the circle. Therefore they are equal to each other. OM equals to 15 and OP also equals to 15. OQ is also the radius of this circle, semicircle, that is 15. OB is also the radius, that is also 15. QB is the line segment that we are looking for in this question. Those two angles are located between the parallel lines QB and PM. QB is parallel to PM according to rule 18. Those two angles are defined as alternating angles and are located between the parallel lines QB and PM. And therefore they must be equal to each other. According to rule 15, those two alternating angles that are located between those two parallel lines QB and PM must be equal to each other. So if this angle is beta, then this angle must be also equal to beta because they are equal to each other according to rule 15. So in the next step I presented to you the law of cosines, and we implemented the law of cosines. This green triangle PQO and this white triangle QBO. So what is the law of cosines? The law of cosines is for an n triangle. This is a triangle ABC. Side AB equals to A unit in its length, side AC equals to B unit in its length, side BC equals to C unit in its length. This is angle theta. In this triangle ABC, cosine theta equals to A square plus B square minus C square over 2 times A times B. In the next step, implemented the law of cosines in this green triangle PQO. So actually, this is triangle PQO, that is according to the original drawing. This is angle beta. According to the law of cosines, in this triangle PQO, cosine beta equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. Again, according to the law of cosines, in this triangle PQO, cosine beta equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. In the next step, I copy this green triangle, and this white triangle QOB in an equation. We implemented the law of cosines in this white triangle QOB. This is the white triangle QOB that I copied from the original drawing. This triangle QOB, cosine beta equals to x squared plus 15 squared minus 15 squared over 2 times 15 times x. Again, cosine beta equals to 15 squared plus x squared minus 15 squared over 2 times 15 times x. So we have two different expressions or two different equations for cosine beta. Therefore, we can have equation 3 that states that cosine beta according to equation 1 must be equal to cosine beta according to equation 2. Cosine beta according to equation 1 equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. And it must be equal to cosine beta according to equation 2. Cosine beta according to equation 2 equals to 15 squared plus x squared minus 15 squared over 2 times 15 times x. So here we have on both sides of this denominator 2 times 15, so 2 times 15 will get cancelled. So in this side of the equation we have 15 squared plus minus 15 squared, that is 0. So we left only with x squared over x, that is x. In this side of the equation we left with 15 squared plus 15 squared minus 10 squared over 15. So in total, according to equation 3, we can find out that x equals to 15 squared plus 15 squared minus 10 squared over 15. 15 squared is 225. So we have 225 plus 225 is 450. 450 minus 10 squared is minus 100 over 15. So x equals to 450 minus 100 over 15. 450 minus 100 is 350. So in total this expression equals to 350 over 15. So x equals to 350 over 15. We divided both the numerator and the denominator of this number by 5. We found out that 350 over 5 is 70 and 15 over 5 is 3. So in total we found out that the length of this 97 cubic that is equal to x is equal to either 70 over 3 units in its length, or in terms of numbers, the length of this 97 cubic, that is the length of this 9 segment cubic that is equal to x, is equal to 23 and 3 units in its length. Okay, thank you very much.